Back in November 2019, I think it was, I made a video about how to get started using the ATTINY10, which is one of the smallest microcontrollers you can buy. Now, I know there are cheaper microcontrollers, such as that 3 cent micro that Dave Jones featured on the EEV blog, but I don't know. I like using Visual Studio, so that's why I use Atmel parts a lot. So I thought I would do a follow-up to that. I actually did testing for this years ago, but never got around to it. So what I want to try to do is make like a really crappy video game using just that chip. Think about a video game, it needs input, it needs output, it needs logic. So what if we create our own NTSC signal? What, you might say? Well, here, let's look at this website. Continue to cite. Oh, I accept your cookies. Thanks, the EU. So this is the basic building blocks of an NTSC signal. And we all know that stands for never the same color. So obviously this is the analog television signal in the US and other countries such as Japan. A lot of modern TVs don't even have composite video jacks on it anymore, but this would be your composite video signal. And remember, it started out as black and white, and then they piggybacked color onto it in the 50s. So this shows your basic thing. You have like 0 volts, or sometimes this would be 0.3 volts. You go below that, below negative 40 IREs, and that's your horizontal sync pulse, and that's how you know that one line has elapsed, right? And then you have a back porch, which is on the left-hand side of the screen before the pixels start. And then you have all your pixels. You have your luminance level. Remember, again, it's a black and white signal with color hacked onto it. Might be fun to do is using that tiny little micro, see if we can generate an NTSC compatible signal. It'll be black and white, but we should be able to get it to work on a TV. And then use that to make a game. Now, we'll have to draw the game scan line by scan line, just like the old Atari 2600, but I think it's doable. So yeah, let's start with some code and the oscilloscope, and then we'll see if we can make this work. At least for now, we're going to use 0 volts for the H-sync pulse, 0.3 volts for the black level, and then 1 volt for the white level. Anything between 0.3 and 7 will be shades of gray, although we don't have enough pins to really do that. So it's going to be literally black and white. It don't matter if you're black or white. Ooh! I've been doing so much programming with the Atmel SAM D21, the Cortex M0 ARM. I just needed a palette cleanser, so that's one of the reasons I wanted to dig this project back up. Look at the good old days when all you had was an ADC, a comparator, and some timers. All right, so here's our ATTINY6, and if you remember, we need a couple of these for programming. Anyway, yeah, let's use PB1 as our sync output. So we only have 4 bits, 0, 1, 2, 3, and then using the high voltage programmer, we can also use the reset line as IO, which we'll need to. So PB1 would be the second bit over. So going back to this, started a basic project here in Atmel Studio 7, 8 million hertz. Okay, and then as we did in the other video, we unlock the protected register, then we remove the clock divider so we get actually 8 million hertz, because by default it'll be 8 million divided by 8, which would be 1 megahertz, which is not fast enough. So the first thing we want to do is do our data direction register B, which is, we have port B. We can write this out in bits. So 1, 2, 3, 4. There's the top 4 bits of that do nothing. 0, oh, I'm sorry. 3, 2, 1, 0. Okay, so that would be set PB1 as output. Right, so we're going to want to use an interrupt for this, right? So let's just do some math. 8 millions divided by the horizontal sync pulse frequency of NTSC for, well, it's called either 15 or 31 kilohertz. So it's actually 15.7 kilohertz, which gives us a duty cycle, well, not a duty cycle, but it gives us a clock time of 509. So with the system running at 8 megahertz, every 509 system clocks, we need to fire this interrupt, which means that's all the more time we have to draw each line. Ha 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 ha, ha 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 ha. Yes, and unlike the Atari 2600, we don't have any graphics registers, so we have to do it all completely manually. Great, so we need to remember the number 509. I'm just gonna grab the clock code from that earlier project. All right, so we're gonna set up our registers here. Again, we talked about this in the other project, but in this case, we want the interrupt to activate, well, every 509 cycles, although I've already tweaked it to 495. So that should give us a 15.7 kilohertz pulse. So we enable the timer, Then we set the high and low register because our time, we're using more than 256 or 255 cycles. So we actually need to use the high and low register to set that to 495 because that would be a 9-bit number. And then we set the bit to actually enable the interrupt. And then SCI actually enables the interrupt to go. But now we need the interrupt. So what we need to do is get the handler for the interrupt. So it's the ISR, interrupt service request, for timer 0, comparator A. So basically when the A counter reaches, when the main counter reaches the A value, it will fire this interrupt, right? So just for now, let's do port B or equals 1 bit shift 1. So that will be set PB1 high. And then we'll immediately set it low. So we'll do and equals the inverse of that. And this will all be, basically turned into bytes by the compiler. So these operations like inverse 1 bit shift 1 they're not actually computed by your chip. The compiler just turns them into static values, which is good. All right, that should be enough to actually get, well, it's not actually the signal we need, but it's the frequency we need. So let's check it out. And we're using the same rig as before, the high voltage programmer for ATTiny, and we're driving it with an AVR ISP Mark II. But now we can try it out. And then I've got my toggle switches, so when you move the switches to the left, that allows you to output the application, and when you move them to the right, that sets them up for programming mode. Suppose if I hooked it up to my scope, that would help. Oh, there's something. Okay, look at that. All right, let's get the measurement. There we go, 15 point, it's a little on the high side, so I could adjust it, but it should be close enough. Again, what can you expect for such a small microcontroller? There's no video hardware in this whatsoever. We're doing it completely with bit banging. Bit banging is where you just use GPIO to perform functions that should be performed by actual peripheral registers. Hey, my voice quality changed again. I don't care. All right, here is the schematic for the first part of this. So here's PV1. Now we're taking it to what we call a voltage divider. Now remember, this is an analog signal we're outputting, so we can't just do it 0 or 1. And 5 volts would be far too high, although we do have to amplify it before we hook it up to a TV, but we'll talk about that later. So what we do is we say, okay, well, we want 0.3 volts. So what we do is we have a voltage divider, so we basically go, only 0.3 away from ground, but 4.7 away from VCC. So, we could compute this, or we could just cheat and use a potentiometer instead of this voltage divider here. So that would look like this. Oh no, my beautiful design. Now this will act the same way as the voltage divider that we just drew. So we're going to hook up PB1 to the wiper, right? And so what we can do is by adjusting the potentiometer, we can change the wiper's relation between ground and VCC, therefore give ourselves an analog signal. However, there is one other thing that we need to do, and that's we need to think about this as an open collector pin. So open collector, that's when you have a pin that you need to pull up resistor for, because the pin by itself won't actually, it can only sink current and can't drive it. So if you have an open collector pin, you can't get 1 volt, 5 volts from it, but you can sink 5 volts. So, well, in this case, we have a voltage divider on it, so it will act as a pull-up. But I'm going to do a trick using the registers that will give us the same effect. Because the thing is, if we just have the circuit sitting here like this, and we don't have it connected, then you'll have 0.3 volts right here, which is our baseline black signal. But what we're going to do is we're going to actually have this pin be an input, right? So if this pin is normally an input, it won't affect this circuit. But if the pin is switched to an output and pulled low, then it will affect the circuit, drawing it to 0 volts, which will give us our H-sync. All right, we're back in the code. All right, so we're going to change this DDRB. We're going to make this a 0, right? So every pin is an input. So I'll just say set PB1 as input, which means it's going to be sampling the voltage on the pin, which means it won't be affecting it. However, I'm also going to say port B equals 1, 2, 3, 4, 5, 6, 7, 8. So if we change the data direction of this pin, it will make it an output. And since we've already staged a 0 as the output register, that means it will basically pull it low. And the thing about that that's good is because we don't really need to do anything to change it. So if we go back up here, well, I mean, we can do it in one operation, not two. GDRB, so we're going to set pin high, pulls sync low, and then we'll release it. So this should give us an inverse of the signal. Oh no, I misspelled DDRB, PBR. All right, reflashing. What? Port B, what? Oh. Oh man, I guess I'm getting old. I can't really see this text very much. I guess I could turn it here. Actually, that probably helps you too, doesn't it? I mean you, the viewer, not the group. All right, I have a 10K potentiometer here. That should work. We can also use this potentiometer to cheat, not having to use an amplifier quite yet, but we'll get to that in a second. So I'm going to attach that side to VCC. Now I'm going to attach this side to ground, unless I knock the cable out of my hands, in which case nothing will happen. Now the center pole of this, the wiper, we're going to attach to PB1. Same thing our scope is hooked up to. And we'll just leave the scope connection hooked up because that way we can see how this potentiometer affects it. All right, let's switch it on. Okay. All right, let's get our trigger. There we go. All right, let's zoom in on that. Okay, cool. We've basically inverted it. See that? I'm going to increase the division factor to 1 volt per division because that's what we need. Also, I don't think this is centered. Yeah, there we go. All right, so we're going to have the trigger pretty low. And let's zoom in even more. Actually, oh yeah, here we go, peak to peak, 750 millivolts. We want, oh man, that trigger's a hair trigger, isn't it? We want about 330. Okay, I found this image on martin.hinner.info/VGA/PAL. So after we've drawn all of our active pixels vertically, we need to basically tell the screen to start drawing over again. So that's what the vertical blank is for. Now we don't have a separate signal for that like you would on VGA. So we do it by having, I think it's either 3 or 9 lines, I'll have to check, of just black. Then you invert it. See this? Where you're going from 0 to 0.3. So basically you invert the H-sync pulse, and that's interpreted as the vertical sync. Then you have 3 more lines of black, and then you start all over again. So what we need to do now is have a line counter. The line counter sleeps tonight. Whip, whip. All right, line counter equals 0, VSync equals 1, and we're going to have these be static volatile because we're going to be using them in an interrupt. We shouldn't do all of this in the interrupt, so let's just do this. Let's create another one. Let's call it line start equals 1. That'll be a flag. And we talked about how the VSync lines are inverted, so let's do this. If VSync, so if we're trying to draw the VSync, we're going to do one thing. If not, we'll do something else. All right, so we already did the if not VSync, which is this. And all we do is we flip it around, and that will give us the inverse. So the reason I had this line start flag is because it's good practice to do the absolute minimum possible in an interrupt. So let's go down to while 1, which is the main loop. If line start, so if we've gotten the flag that a line has started, then let's do some stuff. So this is also where some of the left and right hand side pixel edge hysteresis will occur, because we don't know exactly where we are in this while loop when it triggers, right? So remember, the interrupt happens automatically. So the while loop could be here, here, here. And you know, it's a branching jump, so it takes a little bit of time. And so since this might not be evaluated the same on every line, that's where you're going to have a little bit of hysteresis on the edge of the pixel. All right, so we're in an active line. Great. So let's do some things. Switch line counter. And you should always use switch whenever you can, because I believe it creates an array of pointers, so you don't have to do a bunch of if-then evaluations. It just basically creates a list of where each condition will go to and then jump to. So it's kind of like an on go to in BASIC. Oh, before we do that, line start, clear the flag, increment line counter, which means line counter, when it's evaluated here, will never be 0. It'll be 1 to 262. And you also have front and back porches vertically as well. And that still holds true today for modern LCD controllers and even HDMI. Okay, so let's see. So, well, we know we're going to end at 262, right? Yes, so 262 is the end of the frame. So at 262, line counter, oh, yes, equals 0. So that will reset it. Okay, so we know that. All right, so it's 6 on, 6 off. So see how I'm kind of doing this backwards? So 262 minus 6 is 256. Unfortunately, we couldn't fit this in a one byte number. So that's vsync equals 0. It's being turned off. So that basically creates the 6 lines of front porch for the beginning of the signal. So then if we go backwards again, case 250, which is vsync minus 6, is vsync equals 1. Do you see what we're getting at here? So basically, we're just counting the lines, and at line 250, we turn on vsync. At line 256, we turn off vsync. 6 more blank lines, and then we restart drawing the image. All right, let's give that a shot and see what happens on the scope. All right, it probably doesn't look too much different, but you can see something else is going on. So let's back out. Let's see if we can catch it. There it is. There she is. And not quite as disabled as we were led to believe. There we go. See that? So we inversed it for 6 lines. And that will be our vertical sync pulse. So now we have enough to make a black image on the screen. So I'm just going to crank up the voltage division to make up for the fact we're not using a video amplifier. And yes, this is super jank. And there we go, a black screen. Yeah, it's not the right way to do it, but it does work. And this will at least get us started. Then when we actually build the tiny little console, I'll put in a proper video amplifier, which just requires a transistor. Basically, we just need to separate the video signal that's coming off of our chip with what's going into the display. But this will work for now. We won't be able to get white. We'll get like gray, but it should work. You know, I don't think this camcorder can be killed. It's over 20 years old now. It's been taped under trucks, dropped off cliffs, taped onto jet skis, and it just will never die. All right, I'm going to add a 3K ohm resistor, and I'm going to connect that to PB0, and we're going to use that to basically add the white pixel. Now we're going to do the same thing. We're going to set it up as an open collector, so it will only affect the signal when we want it to. Otherwise, it'll be an input and not affect the signal. I'm going to do this the same way. I'm going to set up PB. Actually, I'm going to use PB2 since I don't have to switch it when I program. So I'm going to set that to be a 1, but it's still set as an input. So again, this pin will not assert a 1 unless we actually switch its data direction register. So normally it won't affect the signal unless we tell it to. All right, so that's going to be, yeah, PB2. So let's do this. Before we actually do the line counter stuff, I mean, this is pretty herky-jerky, but all right, so let's see. We have the back porch and the H-sync. Oh, shoot. Oh, look at this. I got these backwards. That's not good. Oh, no. Where does bad code go when it dies? It doesn't go to heaven where the angels fly. The music in the 90s was like so religious. Do you remember that? Everything was about like angels and crap. You know, like, I'm loving angels instead. All right, so what we want to do is, let's just make it half and half, right? Because we got like half 1 and half 2, even though they're the same value. What a waste. Okay, so we have the back porch, so we've gotten past that. So now we're able to do active pixels. So we're going to set the data direction register of bit or PB2 to be on. So now that 1 will assert itself, which means it'll be basically adding voltage to the circuit. And we're going to delay, what was that called? Half 1. Okay. Then we're going to basically invert that. And then we don't even need to delay again because let's just go to the end of the line. Now that should make half the screen white. Let's see if it works. We'll look for it on the scope first. Okay, what have we done? What have you done? Oh, that's because I didn't switch over the sync. There we go. Oh yeah, that's what we want. See that? Oh yeah. Yeah. There's our H-sync, back porch, half the screen of pixels, well, a little less than half. Half the screen of black, and then the next pulse. And since that will only happen, oh wait, no, I think we need to change it so that that doesn't happen. Oh yeah, see, it's getting confused. It's trying to do that in the vertical pulse, but we have to prevent it from doing that. All right, I'll switch that code basically to tell it not to draw the horizontal pixels when it's in the V blank, and then it should work. Let's do this. If pixels, your favorite movie, so if pixels are enabled, then we draw pixels, else we don't. Okay, just like that. And then what we do is, let's see, what is it? Oh, okay, yeah, right. So we had VSync at 250, which means we have 6 lines of vertical porch behind that. So we would go case 244 and disable the pixels. See? Yeah. And that means we'd also need to enable the pixels. So case 1, yeah. Pixels equals 1. I think I might have a few too many blank lines, but that's okay because it'll be off the top of the screen anyway. All right, so yeah, so it's not trying to draw the pixels during the V blank. All right, let's see if it looks like anything on the screen. Well, we got something on the screen. Doesn't really look like what we wanted. It looks like Yara's Revenge. I'm going to go, let's see, case, it's like 10. Pixel valid equals 0. I know that sounds a little weird. Then up here, if pixel valid is less than how many pixels we want to draw, then draw some pixels. So we'll waste some time, then we'll draw a line and then turn it off. Let's do like, I don't know. Well, we could do probably about 200, I suppose. Yeah, let's be safe. Let's do 150. All right, yeah, let's send that and see what we get. Hey, we get a bar. Our graphics are almost up to the quality of PlayStation 5. What kind of game could we make? Like a Kaboom, where you're trying to catch something? Because we only have 4 pins, so a potentiometer dial as the input would be a good choice, which means we would need to use the ADC. Before we do that, all right, let's back over here, case 10. So let's see what it'd be. 244 would be the bottom. So I'm gonna guess maybe like 220. And then let's make, well, I mean, this isn't exactly how we'll do the whole thing. Let's just see if we can make that more of a paddle, like a bar, or like a flat bar. You know what I mean? Let's see. There we go. Yeah. So maybe we could make stuff drop down from the top, and then you have to catch it, kind of like Kaboom. Here's the updated schematic. We have our white pixel line PB2 going through a resistor, which I think has like maybe 3K on the breadboard, and that's being attached to what I've now called the composite video line. Over here, we have the potentiometer that we want to use to control our character. We have the wiper of it attached to the reset line, pin 6, which is ADC3. And one side of it goes to ground. The other side of it goes through a 20K resistor over to VCC. The idea here is the potentiometer will only affect the bottom third of the ADC, which means we can use the top 2/3 of the ADC to detect if a button's been pressed or not. All right, looking at the data sheet, this is ADC3. Something to think about with ADCs is that there's typically only one analog digital converter in your system. The pins are multiplexed to it. Like if you see here, here's your 4 ADCs, input multiplexer, which means you can only sample one at a time. So if you're doing something like where you're sampling ADCs with an interrupt, you got to make sure you're not, trying to sample 2 at a time, because the ADC also takes a little bit of time to process. Right, so look at our registers here. Blah, 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 blah. What there's all, well, let me see your script. Oh, there's all this. Got you, suckers. All right, so we need to say our add mux, so that's going to be number 3. So we're going to take add mux, just copy paste it right out of here. Okay, so we're going to go add mux equals 3. Okay, so let's see. Select ADC3 as our control. Okay. Now we need to disable any digital input on that. So let's see. Okay, yeah, there we go. Disable digital input register 0. Okay, so when the respective bits are set to logic 1, the digital input bit is disabled. Oh, okay, so by default this isn't done. So we actually, here's the default 0, 0, 0. So we need to set that to 1. Of course, it's going to be the 3rd bit, so let's grab that. Go back over here. That equals 3. Oh, actually, we don't need to or equals because that's the only thing we're setting, so who cares? Disable digital on that pin. Okay, now we need to enable the ADC. That's different than starting the ADC. Where is it? Control status register. Okay. ADEN, ADC enable. Okay, that's good. And then let's see. I think the lower ones are the speed. Oh no, the lower 3 are the speed. Okay, what's the division factor that we want? Okay, so this is how fast it runs. Well, we don't have to run it really fast because we can run this before the active pixels. So, I don't know. Division factor 8. Great. Yeah, let's run it at 1 megahertz. Let's see. ADCSRA is, let's just do this in binary. Okay, enable. Then 1, 2, 3, 4, 5, 6, 1, 1. Okay, so enable ADC with div x speed. Well, yeah, it takes the system clock, which is 8 megahertz, and it divides it by 8, and that's the frequency at which the ADC runs. So we don't really need to run it that fast because we're not going to be doing anything else when we take the sample. But when you do start an ADC conversion, it will start the conversion, and then you can do other things in the meantime. So you don't just have to sit there and wait for the result to be ready. You can get on with your life and then have the result trigger an interrupt and then collect it. Okay, AD start. Okay, so when we set that bit, that actually starts the conversion. Now, if we go back, we have all this these case statements for which line we're on. So what we could do is we could actually sample the ADC at the top of the screen before any logic or whatever game we come up with, whatever crappy game we come up with before any of the logic starts. Now, this is what they would do on old systems like the Atari. They would basically do most of the game computations when the picture wasn't being drawn because they had to spend all their time during the active pixel time drawing the image. So, well, in this case, we want to or equal it because we don't want to affect, oh, come on, Ben. Okay, we want to or equal it because we don't want to affect the other bits, specifically the enable bit. And again, we can just go in here, ADSC. So we can actually grab that because that'll be a constant. So that will actually move that many bits to the left and fill in the ADSC thing. And this will start conversion. And now if we want to be really sneaky, instead of just sitting there and waiting for the conversion, we can just grab it on the next line. So see, we could do all of our math before we even start drawing pixels. Okay, let's do this. Let's go up here and let's create another uint8 x position. That's going to be the position of our guy. Or maybe it's a woman, who knows? X position equals, and then we're just going to load the ADCL register. So line 1 or 0, well, line 1. So on line 1, we start the ADC conversion to read the potentiometer, and then on line 2, we collect it. And then what we can do over here is we can actually change this x equals less than x position, so we can use that value to affect how much delay there is from the left to the right before we draw our character. Okay, got my 20K resistor right there. I'm going to attach that to VCC. Happy little clouds. There we go. The other side of that, I'm going to attach this potentiometer. I even put a little knob on it. How professional. The other side or the wiper of that, we're going to attach to PB0, which is also reset. But again, with the high voltage programmer, we can use it. We just have to flip the toggle switch every time we program. And then I'll attach the other side of that to ground, and we should be able to use this as a potentiometer player control. Of course, we'll have to use the ADC, which we'll look at right now. All right, I'm going to move the panel. Oh, look at that, it's moving, yay! Well, the game is ready, ship it. One thing, we need to have a limit because if we go too far to the right, we will mess up, we'll mess up the sync pulse. See that? So we don't want to do that, so we want to limit it to right about there. And I'd also like a trigger, which is why I wanted to have that extra resistor. So what I can do is I can actually, if I have a 10K potentiometer and a 20K resistor, I can make it so the potentiometer only affects like the first third of the range, and then we can have a button which will pull it to high. So if we see that happen, instead of like updating this position, we can like fire a missile or something. I've hooked up this tack switch as our trigger. So basically when I push it, it's going to move the potentiometer all the way to the top range of 5 volts. So if I push it now,
it will make our cursor go into the danger zone, a zone of danger. But we'll just use code, and we'll say, okay, well, if we're all the way at 5 volts, or well, actually for anything above 1/3 of the range, we'll assume the button's been pushed. Else, we'll update the movement of our character. But that's why I wanted to use a value resistor that was twice that of the potentiometer. So that way, no matter what position the potentiometer is in, it will still go above the halfway point of the voltage when the button's pushed. Otherwise, the position of the potentiometer might affect it too much to get a good reading. So yeah, let's take, 256 divided by 3 is 85. So we'll basically say, yeah, for anything above like 128, then we'll consider the button to be pushed.
All right, so I'm actually going to read the register twice. That will save me a local variable. So if ADCL is, oh, you know what the heck, more than 200. Button pushed. Okay, I guess we'll need a byte for that. Okay, so button flag. Okay, so if it's more than 200, button flag equals 1. Else button flag equals 0, and read the ADC. And I'll have to change the ranging math here, but right now I just want to check the button. So I guess the question is, okay, what happens when the button's pushed? So let's see. Well, we start drawing our, no, wait. Oh yeah, we start drawing our guy at 220. I guess we could change the shape of our guy to show that the button's been pushed. Let's see. This is a bit clunky, but case 100. If button flag pixel valid equals 0. And then we'll just for now, if not button flag. So yeah, that should change the height of our character based on if the button's pushed or not. And then the character shouldn't move because, as you can see here, we're either going to update the character position or set the button flag, not both. So if you do press the button, it won't update your character's position, which means it will be valid when we actually draw it. It'll basically be based off its last known position, which also means, yeah, you can't move your character and push the fire button at the same time. Oh, such limitations for this 20-cent chip. And then Dave Jones shows up. He's like, Mike, you can get a chip for 3 cents from China. I think I did something wrong. We have 2 characters here. Well, I doubled the number of paddles, but I seem to have lost control. Oh, remember, kids, always make sure you've got your break statement. See, case 100 happened, and then it fell through to pixel valid. Shoot.
I put in a slim Whitman tape, my wife put on a brand new hairnet. Kids were in the back seat, jumping up and down, yelling, "Are we there yet?" Oh yeah, there we go. Pew pew. Take that, Space Invaders. Wait a minute. So he's in a 53 to soda, but his kids are reading Spider-Man comics, and they have a tape deck. So clearly the song takes place in at least the 60s, right? But so I guess he just was driving a really old car. I mean, well, I can't talk. My car's like 14 years old.
Something else we could do, we could actually get rid of the back porch delay. And that would actually give us a little bit more time. So we eat up that delay, and then that delay that we need will actually be used up by this logic here. So we can actually use that. You know, basically it gives us more time to compute the line. Yeah, see, we can get pretty much all the way to the left. Yeah, I'll probably restrict it so it's about like that far and that far. And yeah, I don't know, maybe it's like he's like gonna catch pots or something. It's like a Kaboom clone. See, it gets a little trickier because if we start moving things up and down on the screen, we aren't just thinking about their X position, we're having to think about their Y position, which means what line do we draw them on? And then that's going to consume more logic, which means, you know, we're going to use up our line time just trying to compute things, to say nothing for drawing the pixels. I was thinking a really good example of that is Mrs. Pac-Man on the Atari 2600. So you have these black lines here on the left side of the screen. That is where they were still executing code before they could start drawing the next row of pixels. It looks like they happen just before the dots, which obviously would take a lot more code than just drawing the playfield. So yeah, you can actually see where they ran out of time trying to draw the playfield, and that's why a lot of Atari 2600 games have those black lines on the left side, is because yeah, it's actually them getting a late start of drawing the screen. And so we could have that same problem here because just like with the 2600, we have to draw everything every line. Another thing we can do is only draw pixels every other line, which would give us more time. The spaghetti is good. I saw a comment with the last video that I was eating while I was filming, and yep, so I'm eating while I'm filming this. Let's see. Well, we've used up almost half of our memory. So it has 1024 bytes or 1K of program memory flash. However, all the instructions for AVRs are 16 bits each, which means you only have 512 words of storage. 8 whole bytes of data memory out of 32. Ooh, that's a lot so far. Remember, that also includes the stack, like when you're jumping to an instruction and jumping back. So um, we can't use all 32 bytes because we need to save some of the top for the stack. I would say we should save at least 8 bytes for that because the stack's going to be it'll be a 2-byte pointer. What do we have? Line counter, that only goes up to 262. That seems wasteful. Let's get the programmer here. 262. Can we make this bigger? Look at Windows. No, look at that. Pfft. Lame. 262. All right, so yeah, that takes up 9 bits, which means we have the top 3 bits available. We could possibly use those for flags. All right, yes, over here, instead of line start, we could do line counter or equals 1 bit shift 15. So set the MSB of the line counter to indicate a line should start. All right, get rid of that. What were we at? We were at 8 bytes, right? So we can get rid of that. We're not just getting rid of that, we're also getting rid of the fact that it defines it as 0, which takes up flash memory. Okay, so down here, all right, so line, so, okay, obviously we have to change this. All right, so if line counter, line punter? Line counter and, oh, what would that be in hex? 8000000. Okay, so if the top MSB set. Okay, so if that's the case, then we will, oh, I think, oh, we can do this in one operation. Line counter equals, watch this, line counter and, what would that be? 7FFF. Line counter equals itself with that bit removed plus 1 to increment it. So what we did was we sacrificed some program space to gain RAM. And we could even get a little bit more crazy than that. We could get rid of button flag as well. We could say line counter or equals. Of course, we have to make sure we clear this. It would be what? 4000. So we set bit 14. Then this would change to if line. Oh man, now I'm burping. Line counter and that bit. And then again, we would have to line counter, and then we'd have to get rid of the bit. So it's like we can save some RAM, but we might actually use up too much program space. You know what I mean? Well, I saved 2 whopping bytes, but I increased the program memory side by 2%. Well, the thing is, I saved 7% of the RAM at the expense of 2% of the flash. So I would say that's a net win. Oh, we could get rid of VSync as well. Where are we at? 50.6. Okay. So bye-bye VSync. It was great knowing you. You know what? I'm just going to get rid of that too. Pixel valid. Oh, shoot. We could put both of those in there. Well, okay. So let's do this. If, once again, what was it? 14. So let's use 13. If line counter and, why do I keep hitting that? Bit 14 else. Okay. So then down here, instead of making VSync equal 1, we would go line counter or equals 1, no, 13, sorry. Okay, and then here we would just invert it, turn it off. So, and equals the inverse. And again, the compiler will compile this for us ahead of time. So that will be, let's see, 1, 2, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Right, so that's what that'll be. So it'll basically and everything but that. So the other bits, including the fire bit and the line bit, would be undisturbed. And then finally, oh man, it's too bad it wasn't 255. Then we could just roll it over, right? Then we wouldn't have to set it to 0. Yeah, all right. So we get rid of vsync. Now how many bytes? Oh, look at that. We saved 2 more bytes. 4 bytes. Oh yeah, only 4 bytes, and we're making a video signal. Oh shoot. Yeah, we have to remember that when we actually switch the line counter, we have to lob off those top 3 bits. So it'd be line counter and 1 FFF. Okay, that should work. Like if I want to use position 14 instead of 13, so I can just define it everywhere right there, and then I could just change it in one place up here. So that's the useful thing with defines. I think I'll probably save bit 13. I won't have that be the button. I'll have that be something else. I could probably pack the button in with the X position. Oh, I actually went back down to 48%. Nice. Wonder if I could save even more memory. I mean, these should all start at 0, right? So maybe this is redundant. I just burped up spaghetti. I don't usually bother putting meat in it because then you have to cook meat. I mean, it's all about the sauce and the cheese and like the pasta, you know. I mean, that's what it's really about. Let's see if it still works. Still works, and oh wow, we saved 0.4%. Hey, that's more than not saving 0.4%. Did I tell you to shut up straight and eat your vegetables? No. I respected your privacy and taught you self-reliance. We can see the 4 bytes right here. 1, 2, 3, 4. One thing the compiler is really good at is using, well, here, let me show you something. There's 16 general purpose registers in the CPU. Now that's separate from RAM. So yes, there's half as many registers as there are RAM. And there actually are 16-bit pairs of registers too. See that? High and low byte. So what the compiler is really good at is if you pass something to a function, you know, like void stuff, uint8, the value. The compiler is really good at actually storing this value in a register, which frees up RAM and then also speeds it up because the system or the CPU can access its registers faster than it can access the RAM, even though it's all on the same die. We should see if there's anything that we could pass off to a function. So it's like we would lose clock cycles, but we would possibly gain RAM, or we could access the RAM faster. Now, if we were doing this in assembly, we could have complete control over that, but we're not. All right, so there's our character there up close. You can see that there's like sloppy pixels on the left and right hand side. That's because the line is not starting at the same time every time. We might be able to fix that actually. Just as an example, so all this stuff that happens under while 1, we can take that out, right? And then we can actually put that in the interrupt, although we shouldn't, but we can. A lot of things in life you shouldn't, but you can. All right, so obviously there's your before, and then I'll just let the camera roll so you can see before and after. Flashing it. And there's your after. Oh yeah, look how much better that is. But I don't know. I don't want to do everything in the interrupt. That seems kind of sloppy. I wonder if we could like time to the edge of the counter. All right, let's see if we can do some bitmapped graphics. I'm going to have a function called draw sprite, and I'm going to pass it player pixel valid, and I've defined that up here. So it's just going to be like a checkerboard pattern. 6 lines high. Okay, so let's do this. Void draw sprite, and then let's see, the data. Now this is a case where the data will be it'll be 8 bits or 1 byte. However, the compiler will put it into one of the registers, which means it won't count against our measly amount of RAM. All right, so let's think about this. So before we were changing the DDRB bits, so let's do this for int, which will also go in a register. Int 0, just, the usual, what is it? Oh yeah, 8 bits. Duh. How many bits in a byte? That changed over the years. A byte wasn't always 8 bits. Sometimes in the olden days you'd have a computer and it might have like 15-bit words. That's typically what they would say is word, not byte. Okay, let's see. If the data and so if the if the LSB is 1, we will set the pixel, else we'll erase the pixel. All right, so DDRB or equals 1 to 2. I changed a few of the pins around, just experimenting with some timers because eventually we're going to try to put sound on this. And then the inverse. Then what we'll do is we will the date, the warrant. Okay, so the data bit shift to the right 1, so it'll basically continually put the LSB, or it'll put the next bit into the LSB, and that way we only have to compare 1. It's a little less math to do it that way. Yeah, so that should appear approximately where the bar appeared originally. And there we go. We got a little checkerboard pattern. Nice. I also have it. It's only incremented the pixel value every other line, so it's actually double height. So that's 8-bit wide. Now, if you think about it, that line increment data is happening after this. So if we get too close to the edge, even if we don't get that close to the edge, we start messing up the sync. It's not even really a sprite routine. It's basically a software serial shift register routine. We could use this for other things like other sprites on the playfield, like if we wanted to make like Space Invaders or something. I'm still not exactly sure what kind of game I want to make. Real video game consoles, they actually work in a similar way. Every scan line, they'll say, okay, what are the next 8 sprites that are going to be on the next scan line? Like 8 was pretty common back in the day. And so they would load them into shift registers, and then they would shift them out as the particular line was drawn. That's why you'd have like an 8 sprite limit in something like the Nintendo, because there's only so much RAM and time to compare all of the sprites for the next line. But of course, in this case, we're doing completely in software, which makes us even more disadvantaged. Because, even ancient hardware like the Atari 2600, even though the Atari only ran at like 1.13 megahertz, it had a video chip, which means it's still going to beat this thing every day of the week. Oh, look, maybe it's like a picnic game, right? So you made like a picnic basket and you got to like catch ingredients for your picnic. That might be kind of cool.
Yeah, notice here how some of the pixels are wider than the others. What I believe is happening is that we have a bit of a timing issue with our if-then-for loop. Let's take a look at that.
It seems like when it's not drawing a pixel, it runs a little faster. So what's probably happening is that the if-then statement is probably doing a jump to some other code. And if the if-then is not true, it falls through into the else. And again, it's easier to fall through or go to the next memory location than it is to jump. Jumps always cost a couple cycles. So what we can do is we can just grab one of these no ops, which basically tells the CPU to just do nothing for one operation. And so yeah, we'll basically artificially extend the length of this instruction to make it last as long as this instruction, which should make the pixels squared.
It's still a little short on the end. Oh, you know what it is? It's the loop.
Oh yeah, okay, yeah. So think about it this way. Like let's say you've got this loop going, right? So you execute all this and then you either turn the pixel on or off. And then you bit shift the data 1 to the right. But what's happening is that when you come down here and it turns off the pixel, that's happening a little sooner than if you jumped back here. Because remember, you have to jump back to the beginning of the loop and jumps take time. So I bet if we add another NOP right there, that will actually square up those pixels on the right. Again, we're talking about, this is like cycle, I don't want to say cycle accurate, but the timing of even the 4 next loops is actually becoming quite critical at this point.
Okay, I added 2 NOPs after the loop, and now when the pixels are left on, they have sufficient time to stay on before we actually turn them off for the rest of the line. So that's pretty solid. I could try to make the code a little faster. There's not a whole lot I can do without using assembly. And I do not know hardly anything about this. Oh no! The super battery is dead! No super battery! No! Oh, I'm gonna have to recharge the super battery. This this battery is 20 years old, and the fact that it works at all is pretty remarkable.
I've done a little bit more optimization here. I've created some defines, H-sync on when the pulse is on, when it's off, V-sync on when it's off. That's actually just an inverse of H-sync on. And I do this because the defines, well, when we refer to them, it costs us memory space, but it can save us time. So what I did down here was I actually added back two variables, pulse type on and pulse type off. The reason I did that is so when the line starts, we don't have to do any if-thens. We can just dump it right in. I mean, there's only 4 bits on that register, so it's not that hard to map in every possible condition. So the LSB is the H-sync pulse, and then bit 2 is the white on or white off, and then bit 1 is the audio. So we just always leave that as an output. And yeah, we can also do that here for draw sprite. See? So instead of, well, I mean, this isn't really going to gain us. Well, actually, no, it does gain us something because when you OR in a value, like if you do DDRB OR in something, you think about that. It has to read the value of DDRB into a register or in the value and then write it back to DDRB. But with this, we just write a value directly to DDRB. So that should save us some time. And I checked it on the screen. It still works. Originally, I wanted this project to fit within one video, but after editing all of this footage regarding how to generate pixels and make them stable, turns out we jumped up to the 50-minute mark, which is probably about the longest I'd want to make a video. I don't think people really want to watch much longer than that. I certainly never click on videos that are over 1 hour. I don't, unless it's like 8 hours of Commodore SID music, of course. So I'm going to make it 2 parts, even though 2-part episodes don't do as well. So obviously part 1 that we just had was, getting the Tiny set up, adding the circuitry, getting a stable video signal off of it, and getting pixels. Part 2 will be making the game itself, trying to fit everything into the memory that we have and the time that we have. I mean, the time to draw the frame. And then finally in part 2, we'll build the little tiny console itself, which will be like kind of a tiny little tube that fits on the back of a potentiometer. So it'll be quite small. It'll be like half a stick of lipstick in size. Oh man, big lipstick is probably hurting these days, huh? All right, well, hopefully I'll have that video done before Christmas in a couple of weeks. In the meantime, there should be another video about doing accessibility controllers for next gen coming out in a day or two, so look for that as well. It's filled with all sorts of incoherent rambling. I'm sure you'll love it. All right, until next time, hope you enjoyed this and keep on programming.